Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. Today we're looking at lesson 5.5, which is on orbits. Now, we've looked at it quite briefly in that we know that it's force of gravity from the sun on the Earth that keeps it moving around in an orbit, as well as the force of gravity on the Earth on our moon, which keeps it moving around its orbit. So we'll look a little bit more closely at orbits, and we'll go through a typical kind of an orbit type of a problem. So satellites and weightlessness. So when we talk about satellites, they're routinely put into orbit, as all of you know, that there's many satellites that are orbiting the Earth, and the tangential speed of a satellite, it has to be high enough so that the satellite doesn't fall back down to Earth, but it can't be so high that it's going to escape the gravity of the Earth altogether. So you'll have a situation like this where, just don't get hung up on the word tangential speed. It just simply means the speed of the satellite at a tangent of the circle of its orbit. So you have a few different scenarios here. You have a satellite that's a certain distance above the surface of the Earth, and there will be an ideal speed for that satellite to remain in its orbit. If it's not fast enough, if it's not calculated to be fast enough, the orbit will fall down to Earth, and that has taken place. Or if it's calculated to be too high, the satellite will just escape the force of gravity of the Earth, and it will just be lost in space, so to speak. And that has happened as well, as a matter of fact. So the satellite is kept in orbit by its speed, and it is continuously falling, actually, but the Earth curves from underneath it. So you have a situation like this. So the satellite, it falls down toward the Earth. However, the surface of the Earth kind of falls with it, so it just keeps going around and around in its orbit. So objects in orbit, they are said to experience weightlessness. However, they do have a great gravitational force acting on them. You can't just simply turn off gravity, the force of gravity of the Earth. And so what you have is a situation like this. So the satellite and everything within the satellite are in a free fall. And where have we heard that before? The definition of a free fall is the only force acting on an object is gravity. And that's what we have in this situation. So, by definition, a satellite is in a free fall. So there is no normal force on it. And this is what leads to the experience of weightlessness. So any spacecraft, anyone that's been on a spacecraft that's been in an orbit around the Earth will experience a zero normal force, which means that anybody will feel like they are weightless. And again, as we said, that doesn't necessarily mean, or that doesn't mean that there is no force of gravity on it. There is a force of gravity. It's just the force of gravity that's keeping it moving in its orbit, and there is no normal force on anything that's within the spacecraft, or the International Space Station is another example of that, actually. So let's look at what we call a geosynchronous orbit. And a geosynchronous orbit is, by definition, an orbit in which the orbiting object stays directly above the same point over the Earth. So by definition, this is really only possible with points on the Earth that are directly above the equator. And many satellites are launched in this way for various purposes. Often TV, radio transmission satellites are in a geosynchronous orbit, weather satellites, and also some communication relays. So they're just kept basically on the same point above the Earth all the time. So if we look at a typical kind of a problem with this, we want to determine what would the height above the Earth of the particular satellite that is in a geosynchronous orbit, what must its height above the Earth be, and what would its speed be? Because in a geosynchronous orbit above the Earth, it will have to be at a specific height above the Earth, and that'll be true for all satellites that are in a geosynchronous orbit. And then what we'll do is we'll compare that with a satellite that is orbiting, let's say, 200 kilometers above the Earth. We'll just compare their speeds. All right, so here we have the Earth, a nice green Earth. I guess it should be blue. Should be lots of blue in there as well. Anyway, we'll make our Earth green. There's our little satellite over there. And as we mentioned, the satellite, in order to be in geosynchronous orbit, it has to be above the equator of the Earth. And an orbit like this would be kind of like you could actually attach a string from the Earth's surface to the satellite, and it would the tension in the string would remain the same all the time. However, we know that satellites aren't attached by strings, but that just illustrates the situation that the satellite is above the same point of the Earth at all times. So here we have our situation here, and there's a good place to start. F equals ma. Can't go wrong there. So the force of gravity on the satellite is going to be the universal gravitational force constant times the mass of the satellite times the mass of the Earth, divided by the distance squared from the center of the Earth to the satellite. And that then will have to equal the centripetal acceleration, or the centripetal force, on the satellite. So here is our expression right here that will eventually lead us to find the distance as well as the speed. So we don't know the speed, but we know that the speed has to be 2 pi r divided by the period that it takes. And so we can put that into our equation here. So we'll put this in for v. And also, if you notice, the mass of the satellite also cancels out. So in a geosynchronous orbit, all satellites that are in a geosynchronous orbit, it doesn't matter about the mass of the satellite. They will all be at the same height. So the actual mass of the satellite, it does not matter. They will all be the same. Now, we also know that the period, 24 hours is going to equal 24 times 60 times 60, number of minutes an hour, and number of seconds in a minute. And so that will give us that number there. And so then we can put those numbers into our equation here. Now this is just, what this is I've just done the algebra to rearrange this now so that we have r on one side and everything else on the other. So I'm not going to go through all the steps of that. This is just pure simple algebra to get r on one side and everything else on the other. So now we can put all the numbers in here, and we will get r cubed to be this. So then we need to take the cube root of that, and so we get r is 4.23 times 10 to the 7 meters. Now we have to understand that this is from the center of the Earth, and the question was, how high above the surface of the Earth does the satellite have to be? So we have to do that calculation, and you need to always list or read the question very carefully to know exactly what it is asking you. And so in this case, we want above the surface of the Earth. So that's from the center of the Earth. So we have to subtract the from the center of the Earth. Let's see. So then we have to subtract the radius of the Earth, which is, I believe it's 6,280 kilometers. And so when we do that subtraction, then we get this number here, which is the distance from the surface of the Earth to the orbit of the satellite. All right, so that's the first part, and then we want the speed of the satellite. Oh yeah, so here it is right here. So 42,300 kilometers from the center of the Earth, and then we subtract 380 kilometers of the radius of the Earth, and so we get 36,000 kilometers above the surface of the Earth. That's how high the satellite has to be. So the orbit of the satellite then will be as 36,000 kilometers above the surface of the Earth. Now, if you want to find the speed of it, and this should be in your formula sheet, I believe. If not, it's easy to derive. But the speed then will equal the gravitational force constant times the mass of the Earth divided by r. And so we can go ahead and put those numbers in. So notice now that I've got 4.23 times 10 to the 7 here for r, not 36,000 or 3.6 times 10 to the 7. So we need to go back to the center of the Earth for that number there. And when we do that calculation, then we get 3,070 meters per second. So that'll be the speed of that satellite. So any satellite, no matter what its mass, will have an orbit of 36,000 kilometers from the surface of the Earth, and its speed will have to be 3,070 meters per second. So now we'll compare that with a satellite that is 200 kilometers above the surface of the Earth. And so we have to add the radius of the Earth to find the distance from the center of the Earth now, once again. And so the R then again will be 6,580 kilometers for part B of this question. So it's 200 kilometers above the surface of the Earth. It's 6,580 kilometers to the center of the Earth. And that's the number that we'll need for R. So we'll put, there's R for this case. And so now we'll use the same formula that we just did to find the speed of that particular satellite. We'll put all of our numbers into our equation there, and then we get 7,780 meters per second. So a satellite in the geosynchronous orbit, 36,000 kilometers above the surface of the Earth, will have to move at 3,070 meters per second. Now, a satellite that is only 200 kilometers above the surface of the Earth, that will have to move a lot faster because the force of gravity is much faster, hence the centripetal force will be much greater, so therefore its speed will have to be higher, and at 200 kilometers above the surface of the Earth, a satellite will have to move at 7,780 meters per second. So here's an example of orbits and satellites in orbit. This is typical of the kind of question that you have to work with, and so there's really nothing new in this lesson. It's just looking at orbits of satellites now as opposed to orbits of moons or planets around the sun.